I remind you, for those who have posters, that the poster stands are ready now, that the posters must be in by 6:30 because the food caterers are going to take over the tent. And if you have a poster close to the stage, contact Baman Rijai. The next talk is presented by, is submitted by Simon Eng, H. Zhu, H. Permana, S. Lee, and Y. Lu. Simon Eng is making the presentation. He's with the Department of Chemical Engineering and Materials Science at Wayne State University. The talk is entitled Catalyst Characterization by Scanning Tunneling Microscopy, Myth and Reality.
Well, good afternoon. As the title suggests, what I would like to share with you today is the scanning tunneling spectroscopy technique especially applied to heterogeneous catalysis. What I would like to do is more like overview to tell you some of our work that we have been doing in the past 5 years, and also try to contrast is what the myth that you usually hear about this particular technique, and what the reality is, as at least is from our perspective. Now, before I start, I would like to give credit to a group of very dedicated students and postdocs that I have in the past 5 years that did all of this work, very painful STM images, and also I would like to take this opportunity to acknowledge the support from National Science Foundation, General Motors, and Ford Motor Company. Now, here's an outline of my talk. What I would like to do is give you a very brief introduction for the benefit of some of you that may not know what STM is. And then I'll state a number of myths that we hear about of this particular technique. Then I go into drawing on our own experience and talk about all these different systems that we investigated, both in the ambient as well as in the UHV condition. Now, of course, of the time limitation, I will not be able to really go into very deep on each of the systems. But if any of you are interested in afterwards, please feel free that we can talk about it in more detail. But in this particular talk, I just want to give you different flavor of what can be done, what may not be able to be done, or what is difficult to do. And then I will end up by contrast again what the reality is and try to draw some conclusion on that. Now, STM was invented back in 1982 by the IBM scientists, Laura and Bangen, and both of them eventually received the Nobel Prize in Physics. These are the kind of image that started out in 1985 or so that really excited the scientific community as well as us in the catalysis community, because you can see this type of surface topology image can provide us the surface structure, like this is a 7x7 reconstruction. It also shows some sort of defect surface, as well as absorbate on the surface. To me, this is like almost all the things that we're interested in catalysis: absorbate, defect structure, etc. But of course, this is silica. That's not really what we want. Now, STM is a very simple technique. It just involves a very sharp tip that is mounted on several piezos in X, Y, Z positions. And then they use a feedback controller to control the Z position. And the XYZ is scanning across the surface. So as you scan, your Z position moving up and down. So that's how you get the topology information. And if you take a closer look between the tip and the sample, and then what happens is that when this is being very close and when you apply a bias voltage to it, then you have tunneling. The point I'm trying to make here is that the reason the technique is so sensitive is because this is the gap distance between here, is in the exponential term. So what that implies is a very small change in the distance, or the gap distance, will provide all the magnitude change in the tunneling current. So that's why the technique is so sensitive. Now here's our UHV STM system. We had a UHV compatible STM. We had all the transfer system to have a low log in and out, and then we had the standard mass spec, lead OJ, and deposition system, etc. Here we can serve it as a reactive system, so we can also try to run the reaction in a more atmospheric type of pressure, and then we're doing analysis on the pre and post of the reaction. Now, what are the myths? You hear about the STM technique. First thing, of course, is atomic resolution. Second is about it can operate in different environments. It can operate in UHV, air. It can even operate under the liquid or other system. It can provide chemical identity. It can be looking into chemical reactions. You see here Professor Summerjai's talk that already gave you some of those flavor. And then it's a very localized technique, and you can look at practical catalysts. So this is a kind of myth, and then I'll summarize and looking at it afterwards. Now, so let's first look at some ABM system that we look at, the platinum nickel PG, which is a highly oriented pyritic graphite. It's a very standard image. It's 30 by 30 Angstrom, very light, atomic resolution. That's why this particular substrate has been studied to death, is because it's very easy to prepare and it's inert, so you can get atomic resolution very easily in the ABM condition. So what we do is that we can put platinum particles on the HOPG, and then so the first thing STM can do quite easily is to obtain a particle size distribution. Now, in addition to that, we can also focus in small area. For example, an area like this that it looks like you have a big particle here, but if you look closer, then you can see that indeed it's more than just one big particle. Is composed of an aggregate of smaller particles. So this type of information might have a slight advantage over the traditional TEM type of technique that mainly gave you a two-dimensional flavor, but STM can give you more of three-dimensional flavor. Now, we can run a reaction on top of this platinum catalyst. What happens is that we will run a CO-NO reaction on it. And in additional to the CO-NO reaction, we found that it can also have a gasification on the substrate itself, because the substrate, after all, is just carbon. So for this type of study, we can see that the platinum catalyst will eventually fall into the channels, and then it will move around the channel and running along it and bigger and bigger. And then we can have a higher resolution of this type of channel, and then you can see indeed the bottom of the channel is still the graphite substrate that we can observe. So we know that it's running a gasification. And Professor Lanny Smith from Minnesota have done a very elegant work on that, studying all the kinetics of the gasification. So that's another way what STM can do. Okay, let me switch the gear to some molybdenum sulfide. We all know that it's a very important hydrodesulfurization catalyst. In the molybdenum sulfide, it has a layer structure, so we have a sulfur structure, molybdenum structure, and a sulfur layer. And it will depend on which crystallographic plane that you're going to go over. Then you may have sulfur atoms on the sides, or you can have sulfur molybdenum, sulfur molybdenum. So let's look at it. When we take an STM image, we can also know the atomic distance of this. So indeed, this is a 50 Angstrom image. What we can see, if you have good eyes, that in additional to the major atom here, you do see a secondary atom that's right next to it. So it shows that just from topology itself, it provides a little bit of chemical identity to show you which one is the sulfur atom, which one is the molybdenum atom. So if we take the cross-section profile across this, as I showed earlier, that indeed if across 110 cell, you see primary, secondary atom, primary, secondary atom, primary, secondary atom. But if you take it across the other row, then you see mainly the sulfur atom. Now next, what we try to do is that we deposit some of the molybdenum oxides on the surface. So this is the molybdenum oxide. So the point here, though, is that it's very difficult in the ambient condition to really able to extract or have atomic resolution, because it will be a lot less order, and also you have a lot of surface contaminant that will absorb on the surface. That will be different when we do this thing under the UHV condition. Now, but we can sulfurize this particular image. And what happened is that we found that we can convert the molybdenum oxide to molybdenum sulfide, And indeed, interestingly, we see the transformation from more a spherical cluster into a slab-like molybdenum sulfide structure. Now below is molybdenum sulfide because we can take an XPS, and then we can see the changes of the molybdenum state, the changes to the from +6 to +4 state, changes from oxide to the sulfide form. Well, I can't go into too much detail, but this table just want to summarize and say the STM work that we did on all these molybdenum cobalt catalysts compare quite well with other studies using XRF and also high resolution TEM. Now next I want to move to some ultra vacuum study on the molybdenum system, and also after that I will show you some of our most recent work. It's kind of exciting that we do see the absorbate, the molecules themselves on a rhodium-111 surface. Now first on the molybdenum. The white features that you see here are the molybdenum cluster that we deposit using vapor deposition on the surface. It's kind of fuzzy, it's not very well ordered, but what happened is that when we anneal this surface, then you'll see that it will become a little bit better order on the surface, and there are several interesting things you can learn from this type of image. One is that the cluster seems to form a triangular shape. Now, you have to notice that the triangle is pointing a different direction, so that means that it's not just due to the tip is scanning to forming the triangles. It's due to the substrate interaction. But if you look at a bigger cluster than this, okay, this is a small one, but a bigger one, then the bigger one will tend to form a more spherical shape. So what it implies is that even for graphite, it's supposed to be very inert, but when you are small enough, you are still following the substrate of the graphite. Now the other features that we will talk about a little bit more is we see some big rows along of the substrate. We'll see it here, we see it here. Now, a lot of times STM is a technique that contains a lot of artifacts. So you really have to know what you are seeing and how do you interpret that. Now, we know this is not just graphite. Graphite is like right here, because we can always measure the atomic distance between them. But this is much bigger. It's square root 3 times that. So we'll talk about that in a minute. Now this cartoon shows that what happened is that why we have triangular shape of the cluster is because it follows the FIFO symmetry of the graphite on the substrate. So polycarbon is a catalyst also for the HDS reaction. So if you think that the you need to create more edge and corner size, then you know that you need to prepare a smaller cluster that below like 25 angstrom, then you will have more type of edge or corner size. Now, the big rows that I indicated earlier, these are due to electronics effect. It's not just the surface that we are looking at. Why there's electronics effect there is because graphite itself is a layer structure with 3 electrons on the surface. So you have these 3 electrons running around generating an electron wave, and if you had a cluster there sitting there, you will have an incident and reflected wave, and then they will superimpose and then generate this so-called the superstructure effect. It's purely electronic. Now we know that what we observe is true is that case because we can plot it as a function of distance, and this follow the quantum mechanics that predict that this will be decreased as inverse as the distance. So that's indeed what we found, the intensity of those superstructure are decreasing too. Okay, switch gear again. This is still moly and graphite, but this time I show you another things that the STM can do for you, is we can measure the diffusion coefficient of these clusters. So notice that this is cluster A, cluster B that we label. We move the next image, all these things shift a little bit, B come to here, C start to appear. Move the legs, it will B disappear, C come into the place. So that's what we try to monitor here. Now, then we plot all these trajectory of these two clusters. Now you may say, if you know about STM, may say, hey, it seems all moving in one direction. It's just thermal drip. It's not diffusion. Yes, you are right. A lot of this is due to thermal drip. So that's why we'll plot this figure again, taking A as the reference, which is the big cluster. We assume that that didn't move a lot. So therefore, we had a relative motion of the cluster B and C. So we can see the clusters B, for example, move in that, and then move in all this direction, same as in C. So we can use this technique to plot it as a function of the time using this diffusion coefficient equation. Then we can say to deduce the diffusion coefficient of this Morley cluster on the graphite surface to be around 10 to the minus 19, which agree with the literature value of cluster diffusion on the surface. Now finally, I want to show you of the absorbed results on a single crystal. This is a rhodium single crystal. We don't really see the corrugation even under UHV condition. We also have some of the contaminant which we do not know what it is at this point, but we don't see anything from the OJ, and we try very hard to clean it, but that's the best we can come up to. And we see a step surface here. You see the Leak's field images, we all contain them. Now, so now you have this surface, then what we do is that while it's scanning on the STM, we start to emitting the oxygen. So this is 0 to 0.9 lemma. Then the Leak's image is from 0.9 to 1.8. This is a very interesting image. The way that we scan things is from the bottom to top. So the whole thing takes about 3 minutes. So let's focus on the bottom one first. It's still, you don't see much. It's like the previous image. But the second third, then you start to see these rows of oxygen atoms. Okay, starting at forming different islands. Then if you look at the last one third, then it becomes more and more clear of all these oxygen islands on the surface. So it like takes time for the oxygen to come to the surface, dissociate, and then arrange themselves, form on the surface. Now if you take in the Leak's image, then you see now the whole area is covered with the oxygen ion from the bottom to the top. Now all this oxygen ion structure that we have, let's do the Leak's one, is a 2x2 structure because we can measure that, and we know that is 2 times of the rhodium-rhodium distance. And we also try to put a lot of oxygen to it to try to see whether this 2x2 structure will change to 2x1. If you are familiar with the rhodium 111 literature, you know there has been some work done by Summerjai's group or Dr. Fisher's group that they suggest that when you put into enough oxygen, then the structure will change to a 2x1. But STM, on the other hand, shows a very clear picture and suggests that no, there's nothing like that. It's only 2x2. How do we explain the other result? There's a couple alternatives. One is the oxygen is stored inside defects, or whether the oxygen is diffused into the bulk. But I think this shows very clearly there is only 2x2 structure on a rhodium 111 surface. Now, in addition to that, if you have good light again, this is real. This is an anti-phase domain between the different oxygen atom domains. What happened is that this one developed, but then when they come to the edge, they are not the same. But this may help you to see better. What we are saying about the anti-phase domain is that this is one domain, but you have a domain boundary here that does not match each other. Now, okay, so much for oxygen. Now, let's see, put the NO on it and see what happens. NO go to the rhodium surface, it dissociate. And interestingly is that we can see a little bit of the oxygen atom, but we cannot really see any of the nitrogen atom. We know that because we try to put the nitrogen atom along, and we don't see that. Now, and also in this particular image, we were not able to see the NO molecules. But then we do some trick that we learned from General Motors is that, okay, if you just have NO, everything is running around. So let's try to prepare a surface with oxygen first, like maybe half coupling. So in the next image, what we have is oxygen P-absorbed on the surface. These are all the oxygen islands. And then we put the NO on it. Now this time, what we see, all these white spots are corresponding to the NO molecules. This, we believe, is the first time that we observe, in the literature, of our NO molecules. And the reason that it can be done that way is because you form the islands around it, the oxygen island, to trap them so that they don't dissociate to one point. Second point is they don't running around. If they run around, then it will be difficult to image. Plus the fact that we also know that this is not oxygen because now this is a 4x4 structure instead of a 2x2 structure. So what are the implications of this type of studies? If you're familiar with all the NO reduction kinetics, modeling, etc., you see that a lot of time when you write your equation, it's always NO absorbed, react with oxygen right next to it. But this type of image suggests that it may not be the case, may not be homogeneous, that NO and O is sitting right next to each other. As what Professor Samajai suggested on yesterday's talk, that the surface more likely is more heterogeneous, more island formation. And so I think for people that do modeling, maybe you have to take some of this into account of how to do your kinetics. Finally, oxygen again, and this time we put a CO on it. Here's the CO, 7.2 Langmuir. What happened? We don't see the CO, but what we see is that it reacts with the oxygen and forming defects. If we wait a little bit longer, 2 hours after that, we take the image again, much more defects. We don't really see the reaction, but we see how the CO removes the oxygen on the surface. So this is another way that the STM can do to give you a better handle of how the reaction is started or what type of oxygen that the CO would like to breathe first and react on the surface. Okay, so let's go back to the myth and reality. Atomic resolution is really material dependent. It really depends on what you are looking at. I have to say a lot of catalysts that we are interested in, we cannot do it. Mainly you can do it is for things that's more inert, like the HOPG that we're talking about, or the molybdenum sulfide. But if they're inert, we are not interested in that as a catalyst. Environment, again, is related in the sense that if you want different environment, again, if you're doing it in air, you cannot really get atomic resolution, but if you are doing it in ultra-high vacuum, then you have a better chance of doing it. You can imagine if you try to scan a metal catalyst in ambient condition, you have so many things absorbed on the surface, you will not be able to see too much of those structures. Chemical identity, I did not spend too much time on it. This is so-called scanning tunneling spectroscopy. Ideally, you can go there and change your bias voltage to observe a spectra, but this is something extremely difficult to do, especially for metal. So what I want to tell you is that, no, we cannot tell whether there's a rhodium or whether there's a platinum. We can, at this point, only know you just have rhodium or just have platinum and study it that way. But this is an area that will have a lot of potential if we can find out a better way of doing it. For semiconductor, it's easier because they have different Fermi level state that you can image and image out. Chemical reaction, Professor Samajai shows that you can do it, but I think his system is up to about 150 degrees Celsius. So there's a temperature limitation there, and also there's a question of stability when you try to go up higher and higher reaction temperature. Localized, yes, you can see that you can always scan very small area, but actually in reality, that poses a problem is that it's difficult to go back to the same place that you want to look at. That's one. Second is that you don't know whether what you're looking at is really representative of the whole surface. So in order to do that, what you need to do is just ask the graduate student, hey, take more image. Then you can convince yourself that what you're seeing is real or not. And lastly, about practical catalysts, I think at this point, it's not really doable yet. The technique really needs a flat surface so that you can make a good contrast, so that you can look at the corrugation, so that you can interpret your result much better. So I think the challenges here is that we need to, this we already talked about, that basically is that what we can do about it. But I think the challenge that we really need to do is that to start with very model catalysts, with model support, and to try to use those kind of information to apply to the practical catalyst. Now the other thing about variable temperature STM, it will be very powerful. Chemical identity, we mentioned. Also electronic interaction. In catalysis community, we always have this metal support interaction. STM may be able to also pop into that, because after all, the technique itself involves popping the electronics of the surface. So as I indicated earlier, that there are a lot of electronic effects that can be happen on the surface. So this may be another area that STM can contribute. And lastly, this is also interesting things to do is whether you can really atomic engineer the catalyst in a sense that you can use the pulp, use a platinum pulp, making platinum catalyst, but you move the position and then you put a high pulse of voltage to it, then you shoot down a cluster atom, 5 atom, move to a different place, shoot down another 5. So all these are possibilities that provide challenges for us. But I hope that I can convince to you that though STM cannot do everything, but on the other hand, STM is able to provide a lot of other information that is not available by other techniques that we know. This is really local, really surface sensitive, really gave us the structure. You can also look at absorbase, but we can, at this point, cannot really look at the practical catalyst yet. So thank you very much for your attention. I will be more than happy to answer any questions.
That's an excellent talk. Questions?
We've done a lot of these things, including the.
Should you go to the microphone, please?
Ed Wolf, Notre Dame. We've done a lot of these studies, including molar catalysts. Now, one thing you didn't mention is the interaction of the tip with the particles. In particular, you can see in some of the images how the particles move because of the rastering of the tip. In the case of the diffusion study, how can you separate that from the movement of the clusters?
Well, we have been very careful, or at least we believe we have been, to really don't have the tip moving the particle, okay? Because our particle is very small, also it's very fat, it's not a big particle. I think if you had a big particle, then you can really kick around easily. But in our case, we really don't have that. So if on the diffusion study, we look at is that to take care of the thermal drill, see if the tip is moving the thing around, then it's always going to one direction instead of the other direction or going up and down. But I think our data show that it's going all different directions. So that's why we believe we do not have that problem, but that has to be treated carefully so that the tip is not too close to the surface.
George Gallagher from Aristech. Going back to the molybdenum particles on the graphite, where you were showing the electronic artifacts that were coming out of the image, couldn't that be avoided though by switching from STM mode to an AFM mode and repeating the image?
Yes, we believe that it can be done, but we haven't quite do it yet. And plus you have to watch out is that if you do an AFM, you have to use a UH3 AFM too. You can just not use the ambient AFM, then you cannot see the atomic resolution. So I think a lot of people talk about why can't you just use AFM? AFM does not really have all the resolution as the STM. But of course, STM has the disadvantage of that you have to have a conductive substrate.
Dave Kastner, University of Washington. About the molybdenum disulfide, can you vary your tip voltage so you either preferentially couple into the molybdenum or the sulfur?
Yes.
So therefore you can optimize whether you're looking at sulfur or molybdenum atoms?
Yes, you can. But I didn't talk about that. We actually, there's another point about you have to do a lot of careful study in this thing is because you can just by changing your tunneling voltage, In the image that I showed you have primary, secondary atom, you can just see only primary atom or only secondary atom. It's a function of the electronic bias voltage that you put in. Thank you for bringing it up, but yes, that is the case. So that's why the technique is not as straightforward as you think it is. It takes a lot of experience to really understand what you're looking into.
All right, if there are no other questions, then give the speakers today another round of applause, please.